that loss will show up in this term. Okay, you see the minus sign and that minus sign. So the accelerational pressure loss, we combine it with frictional pressure loss. Okay, because it's causing pressure drop, right? So if you want to be more conservative, we use the right part. F sub m, this thing comes from Moody chart. Okay, Moody chart is this chart. There could be a test on this, and it is going to be fair because you studied this already with Dr. something, right? From civil engineer. How do we get relative roughness? Next, Daniel Martinez. I think you get a really good score, did you? Yeah. How do you get the relative roughness?
Take the roughness value divided by 9.
How do you get the roughness value? Chart. If it's not in the chart, we will Google it, right? Use engineering toolbox. Okay. And this C value thing, that is to account for the roughness too, but it's not the same thing as the roughness to be used over there. Okay, calculation of the system pressure. Okay. In this question we have, what is the required power output? This is from Stuart Right-Foot, okay, textbook. From the pump at steady state in the system shown below. There will be a question about this on the exam, very likely. Okay. Water at that temperature, density equal to that much, viscosity equal to that much, is to be delivered to the upper tank at the rate of 12 cubic feet per minute. All the piping is 4-inch, internal diameter, smooth circular pipe. What is the required horsepower on the pump? How do we do that? We use, what is the equation name? Macroscopic something? Mechanical energy balance. Okay, at least memorize the equation name. We use this equation. Okay. First question is, we want to know about W sub m, right? Work done by the pump. W sub m is at the unit of, is at the Strange unit, okay? Work done by the pump per unit mass of fluid is feet square per second square. But what do you want? You want horsepower, right? HP. There's some kind of unit conversion in it, right? You have to be able to do it, okay? I suggest you practice this, okay? Practice, please. It is likely to be an exam. Okay, step 1, calculate the velocity. Step 2, calculate the Reynolds number, okay? Let's take a look at velocity first. We don't use V equal to 60 something 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 because this is for liquid, okay? That one is for gas. So for liquid I use 12 divided by 60, and this is pi d something, okay? What is 12 over 60? I know the flow rate, do we? 12 cubic foot per minute, okay? But if I want per second, I have to do 12 divided by 60, right? Then I get cubic foot per second, okay? And then I divide it by cross-section area. Cross-section area, pi d squared over 4. D is how much? 4-inch. Do we put 4 over there? We have to do unit conversion to feet first before we put over there, okay? So instead of 4, it will be 1/3, right? Okay, 1/3 square or something. This is 1/3. 4-inch. Yes, that is 1/3 of the part diameter. Yeah. So divided by 2. So we have 1/3, 1/3, and 1/2, 1/2. This 1/2 twice is for that, right? So that's why the solution have pi 1/6 square. Okay, I get that much, 2.3 feet per second. Then I calculate Reynolds number. Reynolds number we don't need to do SI, but if we use all feet English unit, we have to keep it like that, and we use this conversion factor Okay, this conversion factor 6.7 to 10 to the power minus 4. Okay, where does that come from? Have you seen that before? Or you can derive that for sure, right? No problem, or maybe a little problem. That comes from this thing that you have earlier, I think. I think it's even previous slide. So that's the conversion factor. We get Reynolds number. Next, we calculate Moody friction factor from the chart. Put it in. What is 5, 300, 100, 120, 20? What's that about? Who want to help me? Next, Ryan. What's his name? Ryan what? Length of pipe. Okay. Total length of pipe, right? We add that with that with that with that. Total length of pipe. That's the total length of pipe. We add them together. We do the calculation. So we get frictional pressure loss. Okay. For the friction factor, if you don't read the chart and you don't want to do this, you see this equation? Smooth pipe. We have friction factor on the left and no friction factor on the right. So this is an explicit form. It's Harlan equation. This equation is very accurate. Okay? And it's good because it's not implicit, it's explicit format. Explicit format means we just plug in the number, no iteration required, and then we get friction factor. Very good. Very easy to use. Okay? Rough approximation, you can do this. If we do C multiplied by Reynolds number to the power of minus n, okay, for the laminar flow case, it is correct, absolutely correct. For the case of turbulent flow case, this is only for smooth pipe. Okay, it is only for smooth pipe. What I'm saying here is there are several friction factor correlation. Okay, the most accurate one is Colebrook equation, but it is implicit format. A little less accurate, but still very accurate, is Harlan equation. Okay, Harlan equation is for turbulent flow only, not laminar flow. Okay, or you can just read the chart. The problem with the chart is different people get different value. It depends on your eyesight, right? If I take off my eyeglasses and look at it, maybe I get wrong value or something. So it depends on eyesight, but it should give you very accurate. But if you want more accuracy, we can do this. Equation will be better only if you know what is that for. So C equal to the top part is for laminar flow, the bottom is for turbulent flow. If you use Harlan equation, Reynolds number more than 4,000 is fully turbulent. Okay. And Moody friction factor is 4 times law of Fanning friction factor. This thing can be on the test. This I can ask you whether it's for laminar or turbulent. This part I can ask you whether it's for laminar or turbulent. Just know that for laminar flow is 64 over Reynolds number. Okay, so that's why n equal to 1 or something. All right. Question. Not much question yet. Still get confused. Get confused, or you have seen this? Okay. I put a note here. Pressure drop per unit length for the above Moody friction factor is only for fully developed. Okay. Near the inlet, minus dPdL or frictional pressure loss per unit length is higher than usual. Okay. Pressure drop per unit length most of the time is the same everywhere. Okay. But near the inlet, there's something we call entrance effect. Okay. Entrance effect means near the inlet, pressure drop per unit length is higher than usual because some part of the energy is used to change the velocity profile shape. To change the shape of the velocity profile. So think about this. First we have a flat velocity profile right at the inlet, right? is flat, it's completely flat. A certain distance away, we have, if it's laminar flow, we have hyperbolic shape, parabolic shape. If it's turbulent flow, we have like 1/7 law velocity profile, okay, like a plug flow. Some length is needed to change the velocity profile from a flat shape to parabola shape, or from the flat shape to the 1/7 law shape, okay. And that additional energy causes the pressure drop per unit length near the inlet to be somewhat higher than the fully developed. Fully developed means velocity profile doesn't change with the length anymore, okay? When I say it doesn't change with the length, and it doesn't change with time either, okay? Okay, the velocity profile thing, for turbulent flow, you see the turbulent flow is more flat, right? From your fluid mechanics, it's a lot more flat. And laminar flow is parabola shape. Okay, one point to note here is this. When we say flat velocity profile, that is time average velocity profile, okay? If we take a picture, snapshot velocity profile is not like that. But if we take several pictures, and average them, on average, velocity profile is like that. You know this, right? Or it doesn't matter for you. So this is to tell you that some measurement that is in the turbulent flow can have some kind of fluctuation. We may not be able to get a particular value, but on the average, we can get it very accurate, okay? Okay, E sub V term, sudden contraction, plane 1, where sudden contraction. Let me go back. Plane 1 is over here. Water in the tank have sudden contraction. Okay, this question is just for like calculation purpose. It's just to demonstrate how you do the calculation. In the actual case, we never put the tank below the pump. Okay, in the actual case, the tank has to be above the pump. Good. Okay. So we have a sudden contraction at plane 1, 3 of 90-degree elbow. Where are those 3? 3 of 90-degree elbow. 1, 2, 3. Right? That's 3 of 90-degree elbow. And we have sudden expansion at plane 2. Okay, sudden expansion at plane 2. It's over here. When it comes, it has sudden expansion. That is the sudden expansion at plane 2. Add all those E sub V together. So we have 1 over 2 GC V squared and summation of E sub V, the acceleration of pressure loss. Then we get the pressure loss of 8 over GC, power force foot over power mass. Okay. Elevation term, difference in height, we put the number in. Pure pressure term, pressure at point 1 and point 2, plane 1 and plane 2, they are 0 psi, so there's no change in pressure term. Okay. Pressure at point 1, atmosphere. Pressure at point 2, atmosphere. Pressure at point 1, atmosphere. So P1 minus P2 is 0. Velocity term, we assume velocity is the same. Okay. From stationary, when it go to tank, it's very slow, so there's small change, okay? Negligible. Put the number in. 0 plus 85 plus 0 equal to that over G sub C over that. Do some math, I get W hat equal to 2830 feet square per second square. Okay. And if I divide it by G sub C, I get 88 power force foot per power mass. Most students get stuck there and get 15 instead of 20. Okay? Don't get stuck over there. Don't be the one who get 15 if you do all the way up here. We have to do a little more unit conversion, okay? Mass flow rate, we know is, we can calculate power mass per second, right? That's mass flow rate. So this is 88 power force foot. Power force foot is the unit of energy Force multiplied by length, that is energy, right? This is energy per unit mass. If we know how much mass we have, then we can multiply them together. Then we have 1,100 power force foot per second. Okay? And there's a conversion factor that will be given, 550. Okay? Horsepower, 550 power force foot per second equal to 1 horsepower. So we can do that conversion and get horsepower. Or if you want more conversion, you get that. Good? Can you do this in the exam? Piece of cake. Not yet? Rohan Agrowal, what happened? You don't like it? Which part that you cannot do? Can you get velocity?
Yeah, I mean, I'll have to go to the example, but I can probably figure it out.
Oh, okay. Alright. Of course, you have to practice. When I see other people swim, I cannot swim, right?
You can't swim.
I can. When I see other people do skating, I cannot do skating. I have to practice. Right? I have to practice. Same, when you see the textbook, I copy this from the textbook, right? Bird do it. Bird short right foot did this. It doesn't mean that you can do it until you practice. Okay? The exam is closed book. Exam is closed book. The formula that given is this and the conversion factor. Make sure you can do it. This is at least 20 points. Okay? Pump specific speed. So this part is about the specification of the pump. If when you see the pump specification and if they talk about the pump specific speed, this is what it means. Okay? We don't really use it until you go to the pump specification and read it. Is that right? Most of the time we don't go that far, but just so you know, this is as a reference. Okay, let's review it a little bit. It is about pump specific speed is calculated as a point of maximum efficiency is used to determine the required impeller geometry. It's about geometry. Also useful in estimating maximum attainable pump efficiency. The lower specific speed, the more the impeller shape we approach through radial flow. So this is about pump geometry thing. Okay, whether we do through radial flow or a little curve like this. Okay, that's about the shape of the impeller. You probably see this in the pump specification. Centrifugal pump. Okay, this chart can be on the quiz too. Like asking you, what happened if we put two pumps in series? What happened if we put two pumps in parallel? Okay, if we have one centrifugal pump, it looks like that. Okay, that's one centrifugal pump. If I have two of them in parallel means we have more flow rate. Okay, so that is the pump curve for parallel. Okay, if I have them in series means one pump after another pump. So doing this doesn't increase more flow rate, but it increases more pressure. So the pump curve go up. Okay, and you need to know that there's a head and there's a flow rate. Okay, good. So the time that we do the pump in series is like this one work as a charge pump. For example, my actual pump may have somewhat high net positive suction head required, NPSHR, and I don't have enough NPSHA, so I need a charge pump. Do you still remember about NPSHR, NPSHA? In the quiz, you should be able to tell what is the full name for NPSHR. Okay, net positive suction head required. Okay, centrifugal pump, inexpensive, no pulse. Okay, lower maintenance cost, small space and weight requirement. That's a good thing with that. Can handle liquid containing some dirt, abrasive, large solid or something because there's no small gap. Can operate at low suction pressure, and we can have variable frequency drive to change the pump speed. Okay, due to the shape of the head capacity curve, centrifugal pump automatically adjusts the change in head. Okay, so the flow rate of the pump depends on how much is the friction in the system. Okay, if we have a lot of pressure against the pump, so a lot of pressure, it will do less flow rate, right? More pressure, we do less flow rate. If we have less pressure drop, we can do kind of more flow rate. Okay? So less pressure, more pressure, it has to do with the size of the pipe, the number of elbow, okay? All of those restrictions that you will calculate. And okay, centrifugal pump is not quite friendly for high viscosity oil. It has self-heating. Okay, only practical for achieving high pressure when there are large flow rate. If we want small flow rate but high pressure, don't use centrifugal pump. Use PD pump. Okay, lower maximum efficiency compared to reciprocating pump. Less efficiency, less pressure compared to PD pump. Okay. Reynolds number calculation derivation. Of course, you will be able to do this because this is a procedure. Okay. Can be in the exam easily. Okay. Okay. How important is the unit conversion thing? Why do we have to go over and over and over this? Because it costs a lot. Okay. September 1999, NASA lost 125 million Mars orbiter spacecraft after this so many days journey to Mars. Miscalculation due to the use of English unit instead of metric unit. Apparently, sent craft slowly off course 60 miles in all. Thruster used to help point to spacecraft had over cost amount of $125 million. Is this important? Yeah. Yes, it is important. Okay, $125 million. So you must be able to do this. Good. Here's the unit conversion. How many horsepower will do? BTU horsepower to this, energy BTU or something. It will be given. Okay. Pressure, 1 inch of water equal to that much. This thing is given. The only thing that you need to know is how. Oh, maybe not all this is given, but length will be given, mass, all this given. Okay. I really have. Okay, I still have some time. Don't go anywhere yet. Okay. Next is pump number 2. Okay. This pump number 2. We have watched the video, and by now you will be able to tell whether it's PD pump or centrifugal pump, right? Diaphragm or something. And next time we will quickly go through all this, okay? And then we will stop a little bit on pulsation control. That is in the exam too. And then we move to the next one. Thank you for coming.